Welcome everyone to another XR Talk Show. We are going to do Wolfram language coding. This is the third take of the Advent of Code 2023, day 14. And yesterday, or the day before, we were doing part 2, and we didn't finish. So today we're going to continue that. And one of the first thing we need to do is to write a function to detect periodicity. Okay, we're gonna code that. If you are watching this offline, skip around and play at 1.5 speed or more, because I ramble a lot, which is often the interesting part. And if you are here, say hi, okay? So let's begin. Okay, so let's start coding. So we did something fun. Let's run the code and show you what we did yesterday, because that's a fun part. So here's a code, Wolfram language. If you don't know Wolfram language, you go to just search for XR Wolfram language tutorial. Okay, and you will find my tutorial. This is designed for programmers, and you can find the download button. Wolfram language is free since 2019. You download the Wolfram engine, and here's a full tutorial designed for programmers. If you are JavaScript coder, Python coder, C or C++, you'll like it. Okay, so let's show. So here we are running the Wolfram language code in Wolfram Notepad. So let's remove this part because this is a personal input. Okay, so here's the code. Here's the input and the code, and okay, and we did the animation. So Shift Enter. Oh, the animation. Where's the animation part? Okay, maybe that's the previous. Okay, so we need to go to this page. This is from yesterday. We did the animation. So let's show that. Copy the code. Select all, paste. Okay, here's the code. Down. We got the board history. And down, and we got those shows animation. So Shift Enter, run it. Okay, we got a problem here. We need to cancel it. Alt period. Because this code, this 1 billion times, that's not working yesterday. So yeah, okay, so let's try this. Shift Control D to split the cell, and we just want to run the first part. Okay, Shift Enter. It'll take 5 seconds because our code is not this manipulate is not done in the most efficient way. So it'll take 10 seconds. But anyway, today we're gonna write a function to detect periodicity of a given function, of a given discrete function. I'm gonna explain that. So we have this yesterday. So this is fun to watch. You can watch, you can watch how the balls move on the board. So let's slow down. So they move north, west, southeast, northwest, southeast, northwest, southeast, and the pattern changes. So it's quite interesting problem. Hello, Huang. Okay, so now we're gonna write a program. Yesterday we made progress, almost solved the problem, except we need the function to find the periodicity. Okay, so copy that. Let's see, yeah. Copy that and go to today's talk show and paste the code here, showing browser. So, not that code. Oh yeah, that's a periodicity. Okay, let's work on that. So yesterday we got a function. This function, someone else wrote it, Richard Phillips, that takes a function and takes an initial value, and it will nest the function, call the function, get the output, and call the function on that again, repeat. And you want to detect the periodicity of the function, meaning that, for example, the function, for example, if you have a function, let's say if you have a function, okay, a function, let's say if it runs, one, it returns 3. Then if it's given 3, it returns, let's say 2. Then if the function at 2 is return 1, then it forms a cycle, because 2 gets 1, then 1 gets become 3, 3 becomes 2, 2 becomes 1. So 3, 2, 1, 3, 2, 1, it forms a cycle. One of the most popular math problem, interesting problem, and extremely difficult unsolved problem is so-called hailstone numbers, so or Collat's conjecture. So let's say hailstone numbers. So let's show that. Hailstone number from Wolfram research. Math world is a very bad resource. You don't want to check any mathematics from the Wolfram math world. That's a very bad and misleading resource. Okay, so here's a Collat's conjecture. So basically the problem is that you define a function such that the function is defined by fn. If n divided by 2 is 0, it's an even number, then you just what is that? Yeah, okay, so here's a better description. If the number is even, divide by 2. Okay, so f4, 4 is even, so 4 divided by 2, you get 2. So f at 4 is 2. Now if the number is odd, then you triple it and add 1. So let's say the number is 5, f at 5. So triple 5 is 15. 15 plus 1 is 16. So f5 is equals to 16. Okay, so this is a function. This is a definition of the function. And so if you keep running the function, you'll notice there's a periodicity. For example, if you begin with, if you at F27, actually this is one of the longest periodic sequence. Basically, the function almost always returns to 0. So it will always become 16, then f at 16 is 8, f at 8 is 4, f at 4 is 2, then f at 2 is 1. So it always comes down to 1. So here's a plot of the function. So the question is, does this function always come down to 1? That is the question, and that is unsolved. Okay, very, very simple problem, but is unsolved. Anyway, we're talking about this problem because we can see there's a period. Okay, I mean, so 168241. So so basically, depending on what number is the input, you become a repetition of several cycles of period. So there's a periodicity. So for example, if the starting value having the largest total stopping time while being less than 10 is 9. Okay, so if f at 9, you got 19 steps and it becomes 1. Anyway, there's a period. Okay, so you can look at this problem. Very interesting problem. I learned this problem while I was in college in 1992, taking a recreational math course. So actually, yeah. So very interesting problem. Collat's conjecture, very famous. You'll see lots of YouTube talking about it too. However, it's not solved. It's very simple, but it's not solved. And some mathematicians say this is, so difficult that today's mathematics we don't have the tools to even approach the problem. Okay, so, and I believe according to Stephen Wolfram, he has talked about this problem in his blogs. Each article is very long. So he seems to suggest, if I recall correctly, this is one of the computational irreducibility. So, so basically his take is that many of these computational problem, this is a math problem, but you can consider it as a computation, as, an algorithm. So what happens if you plug in any number to n? Will it always come down to 1? That is the question. So it's, you can always know the answer by try different n. You can try fn, where n is 1 million, or a billion, or billion plus 1, or gigapetra, whatever big number. You can always just compute it. So any given number, you can find out the answer. Will it always become 1? But the problem is, our computers is limited speed, so there's always bigger number that you cannot just compute. You cannot brute force it. But so Stephen Wolfram is saying, if I believe that he's saying this is one of the might be computational irreducibility problem. So there is no actual theory. So we don't know. We we don't know. We cannot solve this problem. We do not know, or in other words, it's impossible or almost impossible to know. For any number, this will always come down to 1, because computational irreducibility. The only way to find out is just compute. just this is very interesting issue, because hello-based Puffy, very interesting because, for example, when you look at the supercomputers, okay, so it's interesting, supercomputers. Let me tell you about supercomputers. So every year or every few years, they have a list of the fastest supercomputers, and I looked at, this is very interesting thing for me, because I'm a computer nerd, right? I want to see how fast are they, who is creating the fastest supercomputer. So every few years I look at this, and about 2 years ago I looked at it. It's amazing that China has the fastest computer, but they kept quiet about it, because they don't want to be too loud, because when they say, when they join the competition, the USA Americans gets annoyed, because they're gonna like the USA deep state. So China quietly do not publish their speed, which is actually the fastest, faster than the current one, the IBM Blue Jeans. Is that right? I think so. Well, let's look at the fastest right now, so then I can tell. Yeah, faster than Frontier. Okay, I remember. So there's China one. There's a China one faster than this. American Frontier. You will not, of course, you will not easily find the information. No mainstream media will report it. They will just say, look at the American now is back in the fastest again. But actually, you can find the info, but you can find that China, they stopped publishing their speeds. So this is amazing, China, because 5 years ago, starting about 10 years ago, all the top 10 are from China. Very, so we in USA we have a problem now. due to politics and corruption, huge amount of it, the social justice kind and so on. So anyway, it's back to hailstone numbers. So why are we mentioning supercomputers? Because they're so one of the interesting thing about supercomputers, so I look at them, I was wondering, what do they use them for? It turns out the number one use of all these supercomputers is just computing weather. What's the weather gonna be tomorrow? Well, not tomorrow, but next month. And you look into, you think about why, so it turns out the weather is actually the most critically important for human animals today as well as like 4,000 years ago. Because 4,000 years ago, when you don't know it's gonna rain this season or not, you cannot crop, your crop will die. Crop dies, no food. No food, you die. Okay, so weather is like the number one most important thing, weather, okay, 4,000 years ago. Today, two average persons, like us, we don't care. All we care is tomorrow gonna rain because I gonna go shopping or whatever, I gonna go travel and. But however, apparently, the weather is still one of the utmost important thing, because all you look at what all these supercomputers are doing, like half of them or more than half of them is like trying to compute the weather. But for what for? Exactly what for? I'm not too sure. For example, sending Elon Musk sending out rockets, you need to know the weather. Satellites, there's hundreds or thousands of satellites. I don't. So anyway, I don't know exactly why is the weather so important today. So, but apparently it is, because all these supercomputers are trying to compute the weather. So why are we talking about that? Because that's related to the kind of the computational irreducibility, because weather, technically it's, we kind of know how it works, but we cannot predict it, even though the rules are very simple. It's just running a program, but you don't have theories for it. You cannot say in a million years the weather will be this or that. Like, you cannot say it. We can barely say what's the weather next month. The further away the less accurate it is, our prediction. So, and how do we predict? Mostly just by computing it, running weather simulations. Okay, so we want to let's just write. Okay, so let's write a function to compute periodicity. Okay, not PowerShell, Wolfram language. Am I doing good? Laundry will not dry. That's true. Yeah, in Germany, in USA, we don't dry our clothing under the sun anymore. Not in all the cities. We just use the dryers, washing machine. So I don't know if that's the case in Germany. In USA, all the major cities, you cannot dry your clothes because there's no. I mean, there's no room in an apartment also. But even if you have room, usually they forbid you from hanging your clothes in the balcony, because it makes the building look ugly. That's an interesting phenomenon. But if you have a house like in a country towns in USA, I don't think they dry their clothes, because you almost never see it. Like, you can watch American movies, you never see it. It's always just machine, the drying machine, because Americans, we like machines. But it's interesting, because if you look at in Hong Kong, in China, in other countries, Spain, they hang their, or Hispanic countries, South America, they hang your clothes, under the sun to dry, which is actually better. So anyway, let's write let's see, hello, Joman, write a function to detect periodicity of a given function. Okay, that's what we want to do. But yesterday we found this solution from this Richard Phillips from a Wolfram resource function. So you see his solution, I don't think I like it. I haven't tried to test it, but I don't like it because you can see he's using plus tried steps plus. That's like C++. That's a C thing, incremental. So this is not a functional programming code. Okay, I haven't looked into details, but I can tell right away. He's using block. So what is a block? Block means it's like a Lisp-let. It's declaring local variables, but however using dynamic scope. Okay, so this is a dynamic scope of local variable tried steps. So that means he's gonna mutate this variable over. You can see there. So this is not a not a very pure functional programming style. So I'm gonna write my own because I enjoy writing Wolfram language code anyway. So I'm gonna try to do a functional style. Okay. So what is a periodicity of a function? For example, periodicity of a given discrete function. This is important because let's show this again. So why is this what? Oh yeah, so we want to show that. So we were showing that. That's fantastic. Now let's plot sine. Okay. So the most obvious thing about periodicity is, of course, the sine function. Sine x, so x from 0 to 10. Okay, let's say 20. Shift enter. So you see it repeats, every 2 pi. Every 2 pi it repeats. That's the most common example. Let's try something fancy. Okay, let's say plot 3D. So in 2-dimensional, in a surface, into a function of returning a vector, that can also be periodic. That can actually be doubly periodic. Okay, so let's, for example, if we do this, okay, so yeah, so shift that key y from -10 to 10. Okay, let's say -9 to 9. And x from -9 to 9. Let's see what happens. I don't want that. Let's just say that. Okay, so shift enter. So there is a periodic function of sine in 2 dimensions, but this periodic, this one period, but you can have what's so-called double periodicity. Okay, so let's try that again. So let's say sine x times cosine x. Shift enter. Not that. Wait, cosine y. Okay, got cosine y. Shift enter. So there we have it. That's this is so-called doubly periodic because it's periodic in 2 directions. Okay. So I mean, this is a basic example. This is a very intuitive way to understand what's periodicity. The function just repeats. But this is a continuous function. Because it's continuous. But for example, if we have the Hailstone number, that's not okay. The most simple intuitive example of periodic function is mod. Okay, so let's my period x p okay, XPF, okay, God, undecisive about the programming language names. So we define a function, and that function takes a value x, okay, then we say what we are defining a simple example of a discrete periodic function, okay. So mod, okay, most obvious example, let's say mod 5, okay. So let's remove that. Okay, remove that. So if you define this function, let's do a clear, okay, because when you use pattern matching, usually you want to clear it before. Okay, so we define a function. Wait, God. Undo, shift enter, paste here. Am I doing good? Video check, audio check. Okay, so shift enter. So we have a function. Now let's do a table of this function, XOR periodic function. At value x, then x goes from, let's say, 0 to 20. Okay, shift enter. So you can see it's 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. It repeats. Now let's include the input value. Okay, x and then fx. So where is the key for enter? Okay, so there, shift enter. So you can see the pairs of values. 1, 2, 3, 4, 5. So this is a discrete periodic function. Now let's try. Okay, so I'm gonna write a function. So what we want to write is a function that takes a function and determine the periodicity. Okay, so that's what we're gonna write. So let's move this up. Simple example of a periodic function there, and okay, and let's copy that. Let's just copy that so we can see that's a sample value. And now we're gonna write a function to detect periodicity of a given discrete function. Okay, so we want to check period. Okay, let's say x get period. Okay, so that's our function. Okay, clear it. Then okay, how do we do it? Lima, hello Lima, says this is very normal here. Argentina, we hang the clothes to dry in the sun. Fantastic. Using a driver for everything seems pretty energy demanding. Yeah, that's American. That's American life. We we need big trucks, gas guzzlers, and SUVs. Okay, so let me mention another thing. Politics for the MAGA people, make America great again. They say China is the most polluted, using the most gas. But actually, if you go by per person, because China has like 5 times more people, in USA. USA, you have 300 million. The population, about 300 million. Okay, China, they have like 1.4 billion. So 1, 2, 3, 4. So it's like 4 or 5 times more people than USA. So considered as a whole, yes, China uses more energy than USA. But if you consider each person, you got more people, need to more food, right? If you consider each person, then each person in USA is using like 2 or 3 times more energy than the people in China. But we get fake news every day from part of these Trump supporters, these MAGA people. Like every time I say something about China, these people will say, "You are a Chinese 5 cents, fuckheads." This fake news. This very hard to fight. Like every time I have an opinion, that I don't like to see the fake news about China. I'm not even from China. I'm from Taiwan. Okay, but I am Chinese, so I know about Chinese things, culture, history. While the white people, Americans, they know nothing, not a thing. They don't know nothing about Chinese, and of course, they don't speak Chinese. They don't know who are the president before, who are the kings or whatever. They have no idea. But then they say, they say, oh, China, this or that. So sometimes I say that's false. Then they'll just say, oh, you are CCP. How much how much the Xi pays you? Fucking idiots. Okay, so yeah, let's write this function, get period. So how do we do it? So you want to, so let's algorithm description, compute the function at the beginning value. Okay, so the function needs to take a beginning init value. Okay, the function needs to take an init value and oh, wait a minute. Okay, so there's a misconception I made. You see, before we were talking about periodicity of a function. These are examples of discrete function. But what we actually want is the periodicity of nesting a function. So it's not just running a function, through the values, but rather you want to run a function, get an output, then take that output, put back to the function, and get another output. So you want the periodicity of nesting this function, if that exists. Okay, so write the functions to detect the periodicity of nesting a given discrete function. Okay, that's what you want to do. So as for does the sine function is periodic, right? But if you nest the sine function, is it also periodic? I think so. Yes, for certain values it will become periodic. Okay, this is getting more into mathematics. For some value of sine, sine something, then you take the output, then you put it back to sine that. You will. Is that true? Actually, I think so for some values, but that's getting into analysis, into calculus. Anyway, but we just are concerned about discrete function. So again, yeah, so this mod example is also okay. So this mod example is periodic, but is it periodic if you feed, if you nest it? It is also. Okay, so now let's get back to the algorithm. So compute a function starting at init value, nest it for n times. Okay, so for each time you compute the function, save the value. And compare if current value is is in history. Save value as a history list. So every time you compute it, you save the value. So you got a list of previous, values. And but also every time you compute, you want to check. God, this is not so trivial to write actually. Every time you get a new value, you want to check the history list. Oh, this is not trivial to write. Detect the cycle. So you want to check the previous list. If it doesn't match, then that's good. Then you nest it again. But however, if it matches some of the value in the history list, if the current output match a value in history, then you need to make that a state. Then when you compute the next value, you need to check if it match the next value in history. Oh God, this is not trivial to write. So you have to check and check again until you see a match, until you see, until actually until do this check again until an output is the innate value again. Is the innate value is the initial matched value in history list. Okay, so you gotta you have to keep a state. Oh God, how are we gonna do this in functional style? Okay, this is getting complex. We've been talking for almost 40 minutes already. Oh God. Now I want to back out. Let's just use his code. No, I don't want to look at his code. Okay, so we need to write this. So we can always solve a problem just by systematically and do things one step at a time. That's one of the way to solve a problem. Maybe a slow way, but it's a sure way. So you break down the problem, you analyze the problem, and just do, solve one thing at a time, one step at a time. So you want to, so every time you compute this, you want to, so get period, you need a function. Okay, actually you need a function. So given a function and initial value, and then you need some of the max check. Okay, that is the maximum amount of nesting you're gonna check. Okay, so this is not trivial at all. I mean, it's not very difficult, but it's not something you can write. You can write a solution efficiently, fast. So you get period. So that's the that's what the function takes. a function, initial value, and max nest, which is okay. So every time you compute a function, so you want to compute okay. Now I want to write the documentation for this function. Okay, let me show you how to do that in Wolfram language. Okay, so this is how you define a inline documentation for the function. Okay, so you just assign that. So assign that to a string. Okay, so we say that. Okay, so let's see. Let me explain how this works in a bit. So that function return the period of a discrete function f. Return the returns the period of nesting a discrete function f. Okay, and it is the initial value, and the max list is the maximum nesting. Okay, something like that. So this is the inline documentation for this function. Now what does the function do? Let's just say return 3 temporarily, let me show you. So you post this in Wolfram notebook, then you just shift enter, run it, then you can type question mark xget period, then enter, shift enter. So that will give you the inline documentation. Okay, so but now we need to, of course, actually define this. So what do you so what do you need to do? So you need to, so we gotta go back to the algorithm. So every time you compute a function, you save. Okay, so this is gonna be a bit, it's not a trivial code. Okay, so almost always you write a module. Now what does module mean? Module means just like the Lisp let. Okay, so it declares a bunch of local variables, then body here. Okay, this here local variables x, y, and so on. Okay, what's going on? What? Okay, so what do you want to do? So you want to compute f. Okay, so you're gonna do a while loop. Okay, nest while. Let's look at the documentation for nest while. It'll just nest the function until a condition, a function while condition is reached. So here's the documentation for nest while. Okay, f expression and test. Yeah, so this is what, so this is quite convenient, because you see the nest while, they actually provide an argument that is the previous history. Very convenient. So the simple form is nest while f expression test. Okay, let's magnify more. Okay, so the most simple form, give a function that will nest, give an initial value, and test. Test is when to stop. Okay, start with the expression, then repeatedly apply f until applying test to the result no longer yields true. Okay. So if the test is true, it will continue nesting. Okay, let's put that down. Nest while, call the function and the init value, then a test. Here is the important part, the test. So first of all, we can test if a value has already happened before. Okay, first of all, we can test if a value already happened before. Comments, guys. 10 people watching. Comments. Just say hi. Okay, I won't digress onto things, but just say hi. So you want to test. So we can start by. We just want to test if a value has happened before. Okay, in that case, you need, let's see this one. Supply the most recent M results as argument for test. Okay, that makes sense. Then the next one, or supply all results so far as an argument for test at each step. That's what we want. Functional programming supreme. This is a kind of typical way of functional programming of doing a loop, where the function will take the output and feed it back to the function itself. So it's like this is a form of recursion. Okay. So nest while test and okay. So you need a function that's test, and you say all. All means all previous values will pass to the test. Okay. Now we need to define this test. Okay, what this test is going to be, we can define it. Let's put a local variable here. Okay, so we're gonna define ftest. Let's use functional. Instead of pattern, let's use a function. Equals to a function. Okay. Now this x is a list because we said all. So what does it do? That's here. So the test will given a list of all previous values. What supplies all result to so far as argument for test. Okay. So if it returns true, continue. If it returns false, stop. Okay. So of course, then you need a if. Let's just say for now, if length of this list is greater than 5, then false. Okay, otherwise true. Okay, so this function will run basically just 5 times. I mean, this is just for testing purposes, just to be, just so that our function will run, then we have to change this. Okay, so nest while init, run this and use this test function. Okay, then and all previous values. Okay, so when this stops, what does it return? It oh god, so you need, okay, this is not functional, not pure functional programming. Let's say last var. Okay, last value. So this actually will return the last value. Okay, let's just let that be. Okay. Okay, so copy that. Okay, run it. Then x get period. Okay, then we need to define a function. We need to define our mod function. Okay, so yeah, so okay, because we need a function to test. So if you have a mod function, and you nest it, will it repeat? Yes, of course, but how does it repeat exactly? So this is slightly involved. Does that make sense? Hello. So here is the mod. So 2 becomes 2, 3 becomes 3, 11 becomes 1, 12 becomes 2, 13 becomes 3. So let's say if you start with 13, you get 3, then 3 becomes 3, then it's stuck. So you see, when you do this nesting of function, when you nest a function, when you nest a discrete function, the period may change depending on what is your input. Okay, so actually that Collat's conjecture is a good example. The period will change. Is that right, or something? Here's a Collat's conjecture, hailstorm numbers. Okay. So 13 returns 3. If you use the mod, 13 returns 3, then 3 becomes 3, then 3 becomes 3. So for the problem of 13, wait, how do you, what is the definition of a period for our case? 1 becomes 1, 2 becomes 2, 3 becomes 3, 4 becomes 4. So if you start with any of these number, the period is just 1, because 4 becomes 4, then 4 again becomes 4, so that repeats, then the period is 1. Now if you start with 13, then you become 3, then 3 becomes 3, so the period is also 1, or maybe you say 2. But if you start with 20, 20 becomes 0, so they all become, so the period all becomes just 1. Is that right? Oh God. So now we actually getting into an issue. So this if we use the mod function as an example, you only get period of 2, or 1. So we need to actually be more precise. We need to get a clear definition. What does it mean to nest a function and say the function has a period? Okay, it should be simple. You just nest the function and the function come out a sequence of numbers that forms a cycle. Okay, cycle means a sequence of numbers, they just cycle, they repeat. So if 3 comes out 3 comes out 3, that's also a cycle. So how do you define the periodicity? So for the number 3 of this function, of this mod 5, is a period 1 or 2? So let's see, you nest a function, you got a sequence of numbers, and if you find a cycle of those sequence, then you got a period. Then that means this function, when nested, you got a period because the output repeats. Now, how do you determine the periodicity? You take the bunch of numbers that repeat, yes, minus the repeating initial. So in the case of 3 for this function, you just get 3, 3, 3, 3, 3. So what is a period? Well, you take the period which is just a 3 without repeating a 3. So the period would be 1. So for this function, if you start with 3 and you nest it, the period is 3. Is 1. Similarly, if you start with 0, 1, 2, 3, 4, 5, the period is all just 1. Let's see. If the input is 5, you get 0. Okay, then 0 becomes 0 and 0 becomes 0. So you got your 5, 0, 0, 0. So 0 is a repetition, and you take the length without the initial value. So the length is 1. Okay, so any of this input from 0 to 5, the period is 1. Okay, what about 6? So for 6, you get 1, then you get 1, 1, 1. Okay, so the period is also 1. So in fact, for any of these, for this mod, x mod by 5, the period is always just 1 when you nest the function, okay, regardless what is the initial value. Okay, so now we have a better idea. We have more clear, precise definition of a period of nesting a function, and we know now that this mod function, when you nest it, the period is always just 1. So that means this function is not a good example to test our function, because our function, you need some kind of more than 1 period. Okay, so we still need to think about this. So now what about, let's look at the collapse problem. So actually, let's define it. Okay, let's define the hailstone number. Make sure we spelled it correctly. Collatz conjecture is also known hailstone. Okay, so named after the mathematician Lothar Collatz. Okay, introduced the idea in 1937, and sometimes referred to as the hailstone sequence. Okay, hailstone sequence. Let's say hailstone. Okay, because that's more intuitive. Okay, so hailstone function. Okay, so let's define this function, hailstone. Okay, so then we define the function n. Okay, so x, so let's see if I have some so x, if even, if it is even x, then x divided by 2. Okay, otherwise it's odd, x times 3, then plus 1. Okay, so that's we define this function, and we can check. Let's run it. Let's say x is at 27. Okay, then you have to loop it back. So so what you do is you nest list. Okay, nest list will nest a function and return all the sequence of the output. So nest list takes a function, then takes a initial value. Okay, so then we can run this. Okay, so let's put semicolon so it suppress the output. Okay, so let's try it, run it. Nest list. Okay, what looks like we are missing a value here. Let's try. Oh, n times. You need to say how many times. According to, when it's 27, it goes to 11 and 111 steps. So let's say 120. Okay, shift enter. There we have it. So you can see it goes to, return these values, then 421, 421, 421, 421. So there it enters. So there's a period. So what is a period? 421, 421, 421, 421. So the period is 3. Okay. Now if I think we are getting clear what's going on about the nesting period. Okay, so if you start by, let's say, 12, okay, 120, let's say start by 12, shift enter. Yeah, so almost right away you got 421. So the period is still 421. So okay, so I know now, we know this function, the period is always 421. Okay, just 3. The period is 3. Just 3. Okay, so what does it mean when you say of nesting a function, the period of nesting function? Does it depends on the initial value? So for this problem, it does not depend on the initial value. We presume, this unsolved problem will always come down to 1. That has been proven for billions of, like initial value. Like they have tried to use supercomputers to compute it. So, up to what? Up to we have so far we have computed for visualization, then supporting arguments, experimental evidence. So we have computed starting value of 2 followed by 20 zeros. Okay, like 20 zero digit. They all come down to 1. Okay, so we just assume all number will come down to 1. Then the period of this hailstone function is just 3, 421. Okay, and it does not depend on the initial value. Now, what about the idea that some function, some discrete function, such that the period depends on the initial value? Is that possible? Yeah, it is. It's very possible. You can easily have a function where, depending on your initial input, you go to different cycles. Yes, so so we can now make better definition. Okay, so let's elaborate on the let's the period of a function is different from the period of nesting the function. Okay, for example, has period mod number 5 has a period of 5. Okay, because it's always 0 1 2 4 0 1 2 4. So if you mod a number by 5, you have a period of 0 1 2 3 4 0 1 2 3 4 0. You have a period of 5. Okay, but if you nest XPF, then the period is 1. Okay, so that's another, it's a distinction between period of a function versus the period of nesting the function. Okay, that's important thing we realized. Then, I'm doing this systematically. This is my style of solving problems. Usually I don't just code, advance of code, let's just get the answer. So now we're getting into, starting yesterday, we started to notice we need to find the periodicity of a function, of nesting a function. So that's what we are doing today. And we want to fully understand the idea of periodic function and nesting of the periodicity of nesting a function, which is different, very different. Okay, and we have concrete examples here. And also we noticed the periodicity. So what is periodicity? That is just the repeating output. So what is the periodicity? What is periodicity defined? Okay, what is period defined? It means the sequence of output repeats. Okay, that is a periodicity. And next, we also know, is it possible for a discrete function to have a nesting period depending to have a different nesting period for different input, different init value? Yes. Okay, but what about example? Well, so what is an example when you have a function, discrete function, let's say integer function, where the input and output are always integers. And when you nest it, it depends on which. So what is an example for these guys? Guys, tau. Okay, you got any idea? This should be fairly common. Okay, is what is there a math function that have a nesting period, but it depends on the initial value? I think there's a lot, especially when you do chaos, dynamical systems. You have different in different initial value will end up in different cycle. So the cycle is usually called orbit. That's another interesting thing. Dynamical systems. Okay. Not sure what's a simple example, but lots in dynamical systems. So this you can look up, and that would be very interesting. Dynamical systems. What? Okay, search dynamical systems. So that's a branch of mathematics. Basically, this branch, this is one of the most famous example. That is a loop. Okay, that's a cycle that forms a cycle given certain given a function and given a initial value. Then if the initial value is such and such, it'll go into this cycle. This very famous Lorentz attractor. So that's dynamical systems, which actually I don't know much about, but lots of anyway. So that's like a branch of mathematics, and which this is connected to chaos theory, because in chaos theory you want to know at which point, like the initial condition is very important. For some initial condition, they become, this thing. They go into a loop. But for other initial condition, they go into different, loop, which you can visualize. There are few. But however, for some initial value is even if it's a little bit different from the initial value of this one, it becomes something else. And it may never repeat. So that's what chaos theory is about. Just a tiny bit different. Then it doesn't go into so the initial value is critically important. This is like the weather, like the computational irreducibility we talked before. Like weather today, if I didn't do a talk show, then next year there may not be a storm. But if I do a talk show today, if I breathe a little bit harder today, puff the air, then after 10 years there's gonna be a major storm. They call that butterfly effect. So let's just check. So there it is, butterfly effect. Okay, that's a movie. Stupid. This guy, Ashton Kutcher. He's very obsessive about about child trafficking. Okay, but I think he's in trouble. Because of the degree he's into this kind of thing. Usually, these people talking about that, they have a obsession about that. They have a problem. But anyway, so that's a movie. So this butterfly effect. So that is, that's about the butterfly effect. Very interesting. You can go read about it. Dynamical systems. So anyway, so we are trying to find a function where we are trying to find a discrete function where it will repeat given certain initial value, but for different initial value you have a different cycle. But what is the example of such a function? I don't know offhand, so that would be interesting. We need this function because we are trying to because we are writing a function to determine the periodicity. Okay, so this is actually quite non-trivial. Now, in our case, we want a discrete function, meaning an integer. Function takes an integer and return integer. But in many of these chaos systems, dynamical systems, they do have a function, but they are not discrete. Like they are, involving sine, cosine stuff. Geometric definition, real dynamical systems of real, continuous time flow. Okay, those are real numbers and differential equations. Discrete dynamical system. Okay, there we have a discrete dynamic system. when t is taken to be integers, it is a cascade or a map. Okay, so actually we might find an example, but they don't have an article. Okay, then you have cellular automata, which is also, you can consider dynamical system. Okay. Okay, so I bet we can find there's a lot non-discrete continuous examples, but we want a discrete example like of only integers. So I don't know what is that. Okay, we are digressing. So hailstone number, hailstone function, this is an example. This is an example where the nesting periodicity does not depend on init value. It's always 4. Okay, that's the hailstone numbers. It's always 3, 4 to 1, 4 to 1. Okay. Okay, so yeah, we are just digressing. Okay, so now we have a better understanding. Let's get back to write this function. So you call nest while, call the function with the initial condition, then you test it by calling fTest, and you feed the fTest all previous values. Okay. So when do you want to stop? You want to stop when let's write this function. So right now we are just doing this dummy condition. Okay, if it's greater than 5, we'll stop. We can run it actually. So we can run it. Okay, so for example, let's try it. Paste it, run it. Paste the wrong place. Paste it, run it. Okay, now x get period, and we can test it on the function xpf. That's a mod function. Okay, initial value, let's say 99. Okay, and maximum test, let's say 1000. Okay, maximum nest. Okay, run it. Oh, infinite loop. Okay, alt period to stop it. What? Infinite loop. Oh yeah, because wait, if the test is true, continue. What? So let's print, let's debug. Okay, print. Okay, here we debug, we print it. So I don't get why is this non-stop. Okay, so define it. Okay, then let's run this. Let's just say 10. Okay, shift enter. Wow, it's printing a lot, non-stop. Stop, odd period, okay, so it's control period, odd period, okay. It's fucked up. Now it's using up all my memory. Yeah, I don't want to. Shit. It is going into an infinite loop. Impossible. Odd period. I believe odd period is abort. Why is this not? Okay, we force quit. It's not using much memory though, but the program is not responding. Okay, let's force quit. Yeah, it's too bad. Why is this? Did we get the semantic of the true false reversed? Let's see, next while. True to continue, right? Start with the expression, then apply F until applying test to the result no longer yields true. Right, true means continue. So yeah, so this should work. Oh, maybe we got. Okay, let's start Wolfram language again. Okay, we digress so much that today we are not, we didn't finish the vein of code. Third take. So if we paste this here, let's see. Let's double check the precedence. Yeah, those two are together. That should be right. So if it's greater than 5, stop. Otherwise, don't stop. But it's so why is it not stopping? The function. So why is it not stopping? I don't know. Shit, now 3 people watching. All the people gone. So that's no good. So why is this function not stopping? So you got the test, this is a test function, so next while f initial value and test, then pass it all values. Now, okay, let's look at some examples of the test. So even Q stop. Now I need to see an example of the or. Okay, so or print and unsame. So it's a function. Print and unsame. So if they are not the same, what? So actually you can also say apply f at most max times. Oh, so you gotta say, oh, you forgot to say max times here, so that's why it's infinite loop. You need to say max number of times. Okay, then you can apply an extra n times. Okay, then okay, so you got these kind of variations. Now this function, okay, we can run it. So here's a function. Here's a function that is a definition. We run it. Okay, then we now let's rename the XPF. Let's just say X mod 5. Okay, so now we need to define the mod 5 function. So we define it, run it, that's good. Then we test the mod 5 function, paste it, run, that's good. And then then what is next? Then we want to try, okay, not hailstone. Then we want to try then we want to try these. Okay, so max nest 1000. So this shouldn't, let's hope it's not infinite loop. Okay, because this time we added max nest list there. Okay, so shift enter. Okay, stopped finally. So it's just 99. Why is it just 99? Oh, XPF, that's a mistake because you forgot to rename. Okay, delete. This should be X mod 5. Okay, shift enter. Okay, still 99. What the fuck is 99 for? Let's go back. So let's just run 10 times. Okay, shift enter. Initial value is 99. So why is it so you just print 99? So this list is 99. Okay, so something is not right. Yeah. Oh, you actually you need this here. So x list. So the function takes the input x list. X list is always 99. Why is it that we said oh? Let's just say 5. Okay. Let's say nest while list. Okay, this is not right. The test must return true. Okay, so the test function must always return true. So in this case, it's a function that just return true. Okay, so in our case, we can make it yep, that's what I want. So if you do that and list format, what? No. That's what I want. So let's see. Yeah, well, that's just do nesting. And so the function, if the function is true, it always. So if the length is, the length of that is less than 5, then return true. Okay, but you are not getting, so what is this function doing? So that is a problem. Okay, so let's test out this function. Okay, this is let's just always return true, so it always runs. Okay, so this function, we're gonna try this again, and the function will always return true, but however you print the result. Okay, shift enter. So this is the problem. You are always getting the init as input. Oh, okay. So this, when you call, now I get it. When you call next while, and if you say all, pass all previous outputs to the test function. Now, it doesn't pass a list. It actually passes just a sequence of the outputs. That's right. That's right. So, okay, so that's right. Because you can tell, you can test it by, because if you this list is, because here a function, you just say the first argument. Instead, you want all arguments. Okay, so you want all arguments. In that case, you just say, you just say pound sign, pound sign. That stands for all arguments. So now if you do this, you see it prints this. It prints this part. Yeah, that's right. So back over here, and so this list, so this function, you want to get all arguments, so don't use that. All argument just stand for it just stand for so you can do this. 2 pound sign means all arguments. Then you enclose it with a list. Then you got length. Okay. Okay, so we solved that issue, but in any case, this is not the real test. The real test is you get all previous arguments. You want to check if this is different. This is not easy to write because you want some kind of double state. You got the current value. Okay, so here's what you can do. You can check if the all detect cycle. Okay, it's easy. Okay, so here's a list. That's the all previous output. You just want, so given a list, you want to determine if the tail of the list repeats. That's a new problem. Okay, so we break it down. Now we have a new problem. Let's write it out. Given a list, write a determine if the tail of the list repeats Aka cycle. For example, 5, 9, 3, 2, 9, 3, 2, 9. Okay. So write a function to do this. So here's a new separate problem, sub-problem. Once we have that, then we can write our get period function. So how do you determine, given a list, how do you determine the tail repeats? Well, naively, what you can do is you start from the last element and check if that exists previously. If it does, then you start from the second last element, check if that pattern exists. Okay, so here's algorithm. Check if last two element is same. If so, that is the cycle. Done. Okay, that's the tail. That's just basically one single number. Check if last four elements is a cycle, e.g. 1 2 1 2, something like that. A B A B. Okay, if so, cycle is 2. Okay, now otherwise check if 6 elements. Okay, the last 6 element is cycle ABC ABC. Okay, so we started to get a pattern. Okay, so but you always begin at the end, so you do this until the length is less than whatever you want to check. You start with 2 4 6, so that's basically 2n. 2 times 2, 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 2 times n. So you take the 2 times n, the last that count of elements, and basically split it in 2. Yeah, is that right though? What if there's 3 repetitions? Same thing. Yeah, because to determine if the tail, the key is here, tail. So if the tail repeats, you always just check at the end. So you start with 2 elements, then 4 elements, then 6, then 8, and all you have to do is just take elements, split it in the middle, and compare the first part into, so and so on. Okay, and so on. So this is how you would do it naively. Now, how do you do this in Wolfram language? Is there a built-in function? I don't know. So it would be very interesting to check. Let's type cycle. Let's search for cycle. We want to determine if the tail forms a cycle. Cycles represent a permutation with disjoint cycles. Find a cycle. There it is. Wait, that's for graph. Okay, that's more complicated. That's for graph. Find a cycle. Then permutation cycles that generates a permutation cycle. Find Euclidean cycle. That's also for a graph. Hamiltonian cycle for a graph. Cycle length count. Count the number of cycles for all possible cycle length in a permutation. I think that might do. Let's see, show more. Okay, so let's see, let's try, and well, there's also find fundamental cycle. That's for a graph. Now let's see cycle length counts. Ah, God, this is again a function repository, so that's not what we want. Yeah, so that's not what we want. So we want some kind of fuck. Today we're going nowhere. Permutations, okay, permutation cycles, true. Okay, I think this is not do we want permutation? I don't think so. Permutation group, find permutation. So we just actually, we want to detect the tail repeats. So that has little to do with permutation. So what are you doing? So let's go to related guides related to permutation, cyclic permutation representation. Now permutation means given a list of things, you mix them, you reorder them, and you get a list of all possible reordering. So that's what permutation is. And what is a cycle? Cyclic permutation representation. Oh, okay, yeah. So cyclic permutation means that is, that is cyclic permutation. That is a notation to specify a particular reordering. Okay, that's a notation to specify a particular reordering of a list of things, I believe. Oh God, this is not good. Why can we just simply write, okay, this is not good. Okay, we just want to find repetition of the tail. So until is greater than half the length of until n is greater than until 2n is greater than length of least. Okay, so determine the cycle of a tail. How do you do that? God, what is the most efficient way? So permutation is rearranging. This is not about rearranging. So maybe there is no built-in function to do this. Okay, we can write, we can write a function ourselves. So find cyclic tail, okay? And let me just push on. Usage. If none, return empty list. Okay, so that's the documentation. And so we're gonna write the function. Do we want to do it pattern matching or not? We can. No. Okay, so equals to function, then then x is the input. So first of all, you need to get the length. So module. So x is x list, let's say. Okay, so x len equals to length of the list. Okay, now what the body of what you want to do, the body of the function, is that you want to I wanna, God, writing. Okay, this is no good. So why don't we take a break? I sent Wolfram code not related to the problem, but it does not go through chat. No, I think that's because YouTube is YouTube has some kind of filter, let's see, live chat. Yeah, YouTube has some kind of filter that has to do with the setup, like I just follow the normal setup, so it filters, I think it filters code and so on. I can edit, actually. Can I edit? Details, customization, playlist, whatever that. Yeah, so I think there is some kind of trailer, redirect, live chat replay. there is a check mark somewhere about whether to use automatic filter something. Thumbnail playlist audience. Okay, yes, it's not for kid. Okay, paid promotion, no. Altered content, any of the following. Real person doing something didn't say, no. Fake, that's basically fake things. Automatic chapters, okay. Featured places, automatic concepts, tags, recording date and location, license distribution, allow embedding, comments and ratings, okay. Comment moderation, comment moderation basic, okay. Let's say if I say none, save. Now try to post. Let's see if that works. Yeah, anyway, today is kind of, that's no good because I talk too much and no code. And too, like writing simple functions. So we want to find, a cyclic tail. Yeah, so we have to implement this. So you get the list of the length, and so try to post the code, Jolina, see if that works. So we want to find the tail of a function, and so we can follow this algorithm that something like that. Okay, so we can we can use a pattern matching. Okay, so so this would be interesting. Okay, one single line of pattern matching will find you the tail of a list, of a repeating tail of a list. Okay, so you want to do okay. Jolina says nothing. Yeah, I don't know. Something YouTube. So if you want to paste code, even if I change the settings here, I just did, but I don't know if that has a real-time effect, or do I have to set it in before? Comment moderation none. You see. Wait, do I say off? Comment and ratings on. Okay, yeah, so comment rating is on, and live chat, showing live chat, so that's something YouTube, too bad. So anyway, so we want to find the tail. Okay, so what you can do is replace all. Okay, replace all of a given list. Then you want to say head, low line, low line, low line. That's something we don't care. Let's put it here. Okay, head something something. Okay, so actually a list. Wait. So it's a list starting with something 0 or more, anything 0 or more, then tail. Okay, then tail 1 or more, so that's 2 low line. Okay, then matched by tail again. Okay, this will match. When this thing matches, that means there's a repeating tail. Okay, so when that match, just return tail, and tail in a list. Okay, so this would be function. I mean, this would be kind of interesting thing we did today. The first interesting thing. Okay, so we don't need the module anymore. So let's remove the even simpler. Okay, so here is a function. Let's try it. Okay, then all you have to do is try it. So let's say find tail, given a list, 1 2 3 2 3 2. Okay, 9. No. No, because okay, so I think I can fix this. So it should return 3 2 in this case. Okay, so but it's not. In fact, we don't want to use replace all because replace all will check all levels. That's not what we want. We want define a function pattern matching. Okay, pattern matching. Then you want transform function that transform expression by pattern. Okay, here's a list of all of them. So replace all, replace repeated, they all do all levels. What you want is replace with the level spec. That's what you want. Okay, so simply replace, because you can specify a particular level of expression. Level means depth, because expression is an expression can be arbitrary tree. So this is a tricky part of pattern matching. When you have a tree, it just doesn't matter. It does not just match the flat each item. It actually, when you have a tree, it gets complicated. You can read my tutorial if you want. So, but anyway, so we want to say level. Level spec is we just want to say level 1. Okay, but so all we can do, I mean, we can just simply test this expression, and let's say this is that, and okay, in fact this is repeated 1 or more times. Okay, so actually we don't need even that. So this is superb example of the power of pattern matching. Okay, run it. No, failed. This means 1 or more times, 1 or more. So okay, so let's try. Okay, that doesn't work. Why is that not work? It's because So we got 3232. Okay. Tail means so you need some kind of longest. Oh God. Okay, let's try. Longest. Okay, so you got you want a pattern, name this pattern tail. And what is the pattern exactly? The pattern is that longest of one or more, okay, and repeat it one or more times. Okay, this gets complex. Okay, let me get this. Okay, let's try that. What? God, I don't know what's going on. And I'm starting to get tired. Why is this not? So dot dot is repeated one or more times. Let's go back to the pattern matching syntax here, and repeated p max. Okay, repeated a pattern repeated 1 to max times. Okay, so here is the expression repeated. Okay, so let's change them to the full syntax, so maybe it's easier to read. Okay, instead of using the dot dot, let's say repeated. Okay, repeated of this pattern. Okay, so now you can see, now we're getting into this one. So we have a pattern that is that this pattern is named tail, and it's gonna match the longest. Actually, it shouldn't not match the longest. One or more. So yeah, so let's remove the longest for now, because no. God. Oh God, this is very interesting though, but we have failed. So this is a pattern named tail, and the pattern is underscore underscore. So that means it's one or more. So this is just one or more of anything, but you want it repeated. Okay, so I think maybe I should go back to this idea. Okay, so let's just say tail here. Okay, it should work. I won't believe if we cannot solve this. I'm pretty sure it'll just work. There it is. There it is. Okay, so now having understood that, yes, tail, you see, tail repeated twice. Now, oh yeah, all you have to do is put that there. So now let's copy the above, then now do it again, this time just using replace. Yes, it works. The whole expression, 0 to infinity. So anyway, so replace works. Now I want to be sure about the level spec. Okay, so level spec is a bit complex. If you can read my tutorial, there's a example about pattern matching with the level stuff. Level means the depth of the tree. Typically it's a range, like depth 0 to depth 5, but it can also be a specific level, like depth 5 only. So this is important when your pattern can match, arbitrary, like at different depth of a expression. But in our case, we don't want any depth. We want a flat, because we are considering the input as a flat list of items. So if one of the item is a tree and it has the tail, we don't care. We only want to care about the top level. That is why we are using replace. So we can say a level spec. We can limit the level. So level is level n only. So n is corresponding the whole expression. Okay. So level 1 is, we should use level 1. Okay. So we can go back here and we can try. Okay. So if you say level 1, it will also work. No, what? Oh, right, that's right. It needs to be level 0. Okay. Now level 0 is the whole expression. It can be very confusing. Okay. So this works. Now, for example, let's try some other sequence. Now, let's say if the tail is 3, 2, 4. Okay, that doesn't work. That's right. And what if it's 3, 2, 4? That works. Okay. Now, when there's no match, you want it to return 0. Empty list. Okay, so you need to fix this. Find cyclic tail. So if you say match Q, let's see, you want to determine it match or not. so that does not allow you to specify a level. You need to be able to say a level. Okay. Okay, so you want to say replace level 0. Okay, so level 0, and so that's basically just that. Okay, and then you want to say if it didn't match, you need to know if it matched or not. Okay, so there's more detail. Pattern matching functions. Cases, position, count. Yeah, but basically our function works. If it's just that, when there's no match, you'll just return the whole thing, which is not good. When there's no tail, we need to have it return empty list. So we need to apply match Q at level 0. Okay, so we need to apply match Q at level 0. You see, match Q does not have a option for level by default. So that means you need to map at, oh god, this can get very complex. I don't know if you guys know what I'm saying, because map at a specific level. No, the map at is for mapping to a specific list of positions, so that's not what we want. We want to, okay, it's probably boring for all of you. Oh, Jolina finally able to post some code. Oh, it's copy. Can you copy? No. Okay, so let's see. Joman Molina. So map part 1, 2, and what? Evaluate entity country, United States versus China. Okay, let's see. Shift enter. Now this is gonna get some information from the web. This is the using Wolfram language. So you got 340 million people, so that's USA. and the heat, and let's see. Okay, then the second one is 1.4 billion people in China, like I said. So it's using 3.8 kilowatts per person, while in USA it's using 1.35 kilowatts per person. So for each person in USA, it's using about 3 to 4 times more energy. Thank you. Thank you for that political part I was talking about before. Yeah, so for each person in USA, it's using 3 to 4 times more energy, electricity, than China. Okay, so back to here. We have this code. I want, so this code is already working. I mean, but all we have to do is, if there's no match, we want to return an empty list when there's no cycle. Okay, we can easily do that by, for example, if match Q, okay, if match Q that, then do the, return this replace true, okay, else return an empty list. This we can easily do that. So just put this part in the true part. However, if we do that, that's not entirely correct. Why? Because this match Q will match all depth of the expression. Let me show you an example, shall we? Because this match Q, for example, let's say, okay. So here's a list. Let's try it. Okay, so wait. 2, 5, okay. 7, okay. Now you see we got a list like this, okay. Now does this list have a cycle? No, because the last two elements is 2, 5, and the one before that is a list. So this element does not have a cycle. However, if you run this match Q, it will match. Okay, let me show you. Yeah, force. Wait, why is it? Oh yeah, so you need something. What? You see, what I was thinking, it will match the 3, 2, 3, 2 there. Oh wait, the match Q will match the whole expression. Oh, okay. So yeah, so there's a, yeah, that's right. Right, the match Q will match the whole expression, not sub-expression. So the match Q actually works the same, at the same level as the replace by default. So this will work. So we just replace the default here, okay. So now our function works. So let's, we can try it again. How do you guys like Wolfram language code? Except you, Jonah, because you know Wolfram language. But I'm wondering how to do all the other people. So here is our function. Now, if we call this function on, okay, we don't need that. So we need a test function. So for example, we need to test this one, run it, that's correct. What about let's say add 2, run it, 2, that's correct. What if I add 3? Run it. Empty. That's correct. What if you let's say 2323? That will be 23. You know. So if you add another number, let's say 4234, 234, you'll return 234. So this, and you can also have triple repeat your work. So this is a great code we did today. Actually the shiny part of today's talk show. So this is great. Okay, so now we can remove all our previous kind of thing. Okay, so we got this function. Now this function is essential for our original problem of find the period of a nesting of a function. Okay, so all we have to do now here, so here's a test. So let's move the function up. So this function, let's move it up. Find cyclic tail. Okay, cut it, move up somewhere. Paste it. Okay, find cyclic tail. Now we want to write this function get period. So the test will be, so instead of this random toy test, we just say if find cyclic tail at wait, let me hold on a second. Yeah, so if find cyclic tail at all the arguments there, a list of all arguments. So if that returns true, then so if there's cyclic tail, then stop. False. Okay. That means stop running the nesting. Otherwise, true, continue the nesting. Okay. So let's clean up this. So this is a test function. So actually now we have this kind of a short. Wait. So if the find cyclic tail at that is equals to empty list, okay, then that means there's no cycle found. Okay, when there's no cycle found, you want to continue. Okay, so it's a bit annoying here. So anyway, so here is a function to test whether you want the nesting to continue. If the cycle is empty list, then continue. Otherwise, false means stop. Okay, so that is a test function, and we pass the text function to nest while. Okay, good. Now let's test this. Let's copy that. Okay, copy that, and actually we're going somewhere now. Finally we actually, so this code, run it. Okay, it ran. So what so what is this part? What is this doing? X get period, X mod 5. Wait, there's something not right. Okay, let's restart Wolfram language. Okay, so let me do some screenshot. because that's some of the interesting parts for today's talk show. Okay, then we're gonna restart Wolfram language, save, no, and close that. Okay, now it's 2 hours and a half. New notepad, 3, shift enter to evaluate, magnify. Okay, now we have several code we want to try. This you don't need, so copy that, hailstone, and copy that, and find tail, yes, then so copy that, or select or paste. Okay, so here is today's. So we got mod 5 function, then we got some clarification of periodicity versus nesting of a function periodicity. Then we explained how to precisely define periodicity. Then we explored on the question, is it possible to have a discrete function whose nesting periodicity is dependent on the input? Yes. However, we don't have an example. Then we have hailstone numbers, which is a discrete function that has a periodicity of 3 always, not dependent on the input. Okay, so hailstone number defined, and why do they put the red correct there? Oh, because you are missing, let's say nest list 10. Okay, then you have find cyclic tail. Okay, let's separate each. And because this is so slow today anyway, so why not just, okay, so you can run that, see example. Okay, go down, and here's a hailstone numbers, split, and run that. So that's the example. Then you got find a cyclic, very good. Now, do we have a test? No, so we need to get a test. Yeah. Did we? Okay, we have to rewrite it. Nine, 3, 2, 3, 2. Okay. Split. Shift enter, run it. Here's the example, run it, 3, 2. Now if you got 1, that returns empty list because that's not cyclic. Okay, so now we get back to this function, get period. Determine the period of a function when nesting it. Okay, and this is the goal of today's talk show, and looks like I got it. It looks like how elegant it is. Compare this. Although I was slow for 3 hours almost, but compare these to the one someone else wrote. To the one someone else wrote here. So if we are successful, that means truly elegant. So this is someone else's code. Richard Phillips from function repository. But our code is just this, okay? But we haven't tested for sure yet. We don't know if this is, oh yeah, you need a semicolon there. So this basically we'll call nest while and of a function, apply initial value to the function, then use the test function to determine when to stop. And every time you call the test function, you pass all previous argument to it. And this will stop at maximum nest number of times, okay? And this test function is just this. It tests if all the previous argument has a cyclic tail. If not, it's empty, then true means continue, otherwise stop. Okay, so that's, but when you stop, you just stop. You still need to know the length of whatever this returns. So we still need to modify it. Okay, but I think that's it. 99.9% sure this is correct. So yesterday, it's like yesterday after 3 hours, we determined we need this function. The function is already there, but actually we tried it, didn't work for some reason. We still don't know why yet. So today we made progress by writing this function ourselves, another 3 hours, but we did it. I mean, well, not yet. But I'm 99% sure it works. Then maybe tomorrow, I think next one I'm gonna do some Emac Lisp. But then we do next one, then we finish this, and then we can go back to testing our vein of code, the matrix. And does that make sense? I don't think anyone is following me anywhere by now. Okay, 5 people. Okay, so that's it. So why don't we continue this? No, because we need, in order to test this function thoroughly, we need to find a function where when you nest it, we need to find a discrete function that takes a, let's say integer or a matrix of integers. An integer and return an integer, or a matrix and return a matrix. Actually, we do have that function from a domain of code. So anyway, we in order to test this, we need to find a function, discrete function that when given certain initial value, it has a cycle and a period. Okay. Yeah, in order to test that. We could easily create that function just by defining brute force values, to make it cycle. Like just hard code, when it's 2, return 231, things like that. When it's, 10, return 1031, 10312 cycle. So different input will have a different periodicity and the list of cyclic tail. Yeah, we can hard code it, but I don't feel like doing that. So I think that's good. Thank you guys for watching today. I think that's it for that. Yeah. I'm thinking deleting this video today because it's like close to 3 hours and not doing much. Anyway. Okay, yeah, so that's our code. And what is his code doing? I mean, he's he's using not pure functional approach. He's using the plus plus, there. Plus plus and try steps, that's a local variable, and he's incrementing it using a block, means dynamic scope. Then he's using width. Width is a constant, okay? Declaration of constant. Okay, so he's doing nest while, and you can see, yeah. So I think the way we did it is much more better, and I would claim also faster. Okay, so yeah, this would be a good problem. So next video we're gonna thoroughly test out, create a function that is cyclic when nested, and depending on different initial value, you have different periodicity and different cyclic tails. So we get a simple function, we try to find it. Then we compare these two solutions, and we can test the speed. Okay, that's it for today. Thank you guys for watching. Bye. Put this back. Syntax correct show. So this is what we did today. That's close to 3 hours, but a lot of thinking. That's kind of typical for programming. Bye.